Hi everyone, my name is Gary Hu. I'm from the Argonne National Lab, and today I'm presenting a PDE-based jump estimation for phase field regularized cracks. Uh, I'm first going to briefly talk about why we need this jump estimation. The jump over a discontinuity is an important quantity in many physical phenomena. So, for example, in cohesive fracture, we need to know the separation in order to consider the traction separation law. In hydraulic fracturing, we will need to know the crack opening displacement to compute fluid permeability. And in thermal contact, we have COD dependent thermal conductivity and temperature jump dependent heat flux. And in electrodynamics, we will need to know the distance between the separators and the jump in the electric field to compute the redox condition or the Butler-Mummer jump condition. The list goes on. Um, the idea is that the jump is an important quantity. So with sharp cracks, computing the jump is fairly straightforward. For a point where we denote the value at that point u minus, we just need to find its topological neighbor and then denote that value as u plus. Then the jump is simply u plus minus u minus. That's it. But for regularized cracks, estimating the jump is less straightforward. There are two main challenges. The first one being there is no clear definition of a topological neighbor across the interface, right? And the second issue is that the jump uh, isn't very well defined across the entire phase field band. So suppose we have this field value u that has a jump at a location right in the middle, and then at this very point, the jump is well defined, but then the jump isn't well defined at other locations where the phase field is non-zero. Okay, so it is actually straightforward to see that in order for the phase field fracture to gamma converge, uh, the jump value has to be constant everywhere inside the phase field band. So this is what I meant by broadcasting. Once we have the jump estimation, we need to broadcast it over the entire phase field band, and this process is inherently non-local. So that is the second challenge. Um, so just a brief summary of the existing state-of-the-art techniques. The first one, the first approach to compute to estimate this displacement jump is purely local. It is based on the stretch of the element and relying on the strain tensor. The second approach is constructing an auxiliary field to represent the displacement jump. The third approach is probably the most accurate approach because it is a direct regularization of the displacement jump, but it has the limitation that you have to have exactly one straight crack inside the domain, and you know how where you want to perform that line integral. The fourth approach is relying on the level set to interpolate COD. Um, it is also a nice approach, but it relies on a strong assumption that the displacement field is perfectly symmetric about the crack. Uh, the last approach is proposed by Yoshioka, where they construct a set of line elements that are perpendicular to the crack set, and they perform a line integral using those line elements. They also propose to construct a level set to help interpolate in COD at the intersection of the level set and the crack normal, some small distance away from the crack set, and that is supposed to improve the estimation quality. So today, our proposed method can be viewed as a direct extension of the second approach here, where we also compute an auxiliary jump field. the way we compute the jump field is purely PDE based, and we extend this second approach to consider a general jump. So it's not just a displacement jump. And we also propose a crack indicator function to identify where the crack tips are, and so that we can exclude crack tips when we are finding the jump to improve its quality. So next I will briefly go over the basic derivation and some numerical treatments of our proposed method. So so first of all, we make two assumptions. The first one being the phase field has to be compactly supported with W known a priori. That is not saying that this approach doesn't work for 82 where we have exponential decay or infinite support of the phase field. It's just that it's easy to deal with a compactly supported phase field band, so that we don't need to play around with other parameters that we need to tune. The second assumption is that we need, for this approach to work, we need the crack surface normal to be roughly divergence free, and I will explain that momentarily. So the basic idea is that suppose in 1D we have an integrable function, and then we can calculate its integral along a path by projecting it onto a pathwise constant function, and that function I is the auxiliary field we are looking for here, and the pathwise constant constraint can be expressed something like this. Okay, and then the resulting auxiliary field is going to be the integral we're looking for. Okay. And in 2D and 3D, this can be generalized as follows, where W is the width of the phase field band, F is the function we wish to integrate, and N is the crack surface normal, I is the auxiliary field we're looking for, and the pathwise constant constraint is expressed like this. Okay. And then how do we use this to estimate the crack jump, or the jump across a crack? So the jump across a discontinuity can be written as this, where we can use a direct delta function to write it in an integral form. Okay. So the idea is that with a phase field approach, we can regularize this direct delta function with some indicator function I, and then the integrand we're looking to integrate is the value of the field times the norm of the gradient of the indicator function. So if we integrate that along the path, we obtain the jump. So how do we obtain this integral in the general general setting where we have an arbitrary shape of the crack, and we have arbitrarily many cracks in a domain? So we rely on this PDE-based approach that I just talked about on the previous page. So the directional jump can be solved by projecting this integrand onto this auxiliary field subject to the pathwise constant constraint, and then which is the integral statement of the directional jump is equal to the jump in the field variable times the crack surface normal for any point inside the phase field bandwidth, which is compactly supported. Okay. So a few remarks here. The directional jump can be approximated using the finite element method, and the pathwise constant constraint in this work is enforced using a penalty approach, where alpha is the penalty parameter. So so here I'm showing you how the result may look like. So suppose we have a phase field on the left, and then we have a field variable u sub y on the middle. Then the resulting jump in u sub y looks like this. As you can see, it is constant across the entire phase field band, and the value is equal to the jump in the field variable you supply. So it works well for a fully developed crack. It is the simplest scenario, but it doesn't work so well when a crack is embedded. It is not fully correct. It is not fully developed. So it may look okay here, but in our experience in practice, um, the the jump estimation near the crack tip is really bad, and it is polluting the entire jump estimation across the entire phase field bandwidth. So we want to somehow exclude or ignore the effect or the influence of the crack tips. So we propose to find a crack tip indicator function, which is obtained by projecting the phase field onto an anisotropic subspace. And for the interest of time today, I'm not going into too much detail about it, but we will show more details in the manuscript that we're preparing right now. So with the crack tip indicator function, we're able to exclude the crack tips, and the resulting displacement jump estimation is much better. And the third remark here is that on unstructured meshes, sometimes we need a better crack normal approximation. So we can rely on a level set which is reconstructed from the phase field to do that. So this is the same approach proposed by Lee and Wheeler in one of the paper I talked about earlier. So, and then some remarks on the computational cost. So computing and broadcasting the jump across the phase field crack is now fully automated at the cost of solving one or optionally up to 3 additional systems of equations. The additional auxiliary problems are all linear, so they are not all that expensive, and furthermore, the level set and the crack tip indicator functions can be solved on a confined domain where the phase field is greater than 0. Recall our assumption that the phase field is compactly supported. The directional jump can be solved on an even smaller domain after excluding the crack tips. So it's actually pretty cheap. It's actually a pretty cheap computation. Our proposed method also allows for monolithic coupling between the jump and other field equations. So this is the biggest difference between our approach and a geometric search type of approach based on sharp cracks. So next I want to show you some numerical results. So first of all, we look at a square domain with an embedded crack. The bottom is fully fixed, and the top is under is subject to a displacement control. So excuse me, the resulting jump field looks like this, and then as we refine the mesh, the result gets better, and then the blue curve approaches the black dashed curve here, where the blue curve is the jump we obtained using our proposed method, using this PDE-based approach, and then the black dashed curves are the displacement jump measured using the actual field value. Okay, and similarly, we can also do this on an unstructured mesh, or in other words, when the crack isn't perfectly aligned with the background mesh. So as you can see here, as we refine the mesh again, the result becomes better and better. Except that you may see some squiggles here and there. That is the artifact of unstructured mesh, but in general it agrees with the measured displacement jump fairly well. And next we look at a patch test for a more complicated phenomena, which is thermal contact. So in this case, we also bring in temperature as an additional field. So two bodies can exchange energy in the form of heat due to thermal contact. So as the two bodies get close to each other, we may have thermal energy exchange and heat radiation. But for now, let's neglect heat radiation. The heat flux is defined on the right hand side here, where we need to know the displacement jump in order to compute the attenuation of the get conductivity, and we also need to know the jump in the temperature field to compute the heat flux. So the additional jump field can be computed along with the displacement jump using the same algorithm we proposed. The gap distance dependent attenuation of the gap conductivity introduce a thermomechanical coupling. So if we solve this using a traditional sharp crack, we will have to perform a geometric search after every time a displacement field and temperature field are computed. That introduces an inherent lag or decoupling between the physics. So we're not able to take a truly full Newton step, and our preconditioning matrix won't be exact. So so as a result, we may take more nonlinear iterations than we needed. So using our PDE-based approach, we can actually get a fully coupled system where we know how the temperature jump and the displacement jump may change as a result of the field variables, and how the field variables will change as a function of the displacement jump and temperature jump. So the result is shown in this figure. This is measuring the temperature value across the domain in the vertical direction. It is a boring graph because the approximated temperature value matches the analytical solution almost exactly, and it gets better and better as we refine the mesh. So this is a working patch test. So next, the last example we want to show is a comparison between our PDE-based approach using a regularized phase field crack and a sharp crack solution. Okay, so again, here we have a square domain with an embedding crack, which is fixed on the bottom and applied a displacement on the top boundary. We're also prescribing a temperature on top and bottom so that we have a temperature gradient. We measure the solution of temperature in the vertical direction at 3 different x locations. At x equal to 0.1, that is on the left end of the crack, x equal to 0.5, that is at the middle of the crack, and x equal to 0.3 is somewhere in between. And as you can see here in this case, as we use a smaller and smaller regularization length, phase field regularization length, the result gets better and better, and it approaches the sharp crack solution. So finally, some concluding remarks. A PDE-based approach is proposed to compute the general directional jump field. The performance of the algorithm can be improved by excluding crack tips and reconstructing a level set for better crack surface normals. This is important if you have an unstructured mesh or the phase field doesn't perfectly align with your background mesh. The additional subproblems are cheap as they are linear and can be solved on subsets of the crack set. So it's a really small confined domain compared to the entire computational domain. Numerical examples show that the directional jump approximation improves with mesh refinement, and the proposed method works on both structured and unstructured meshes. The proposed method is also used to model phase field fracture with thermal contact. The solution matches analytical solution in the patch test, and the solution converges to the reference sharp crack solution as the regularization length diminishes. So with that, I would like to thank the Argonne National Lab, the Idaho National Lab, and Duke University for supporting this work. With that, we can conclude this